a large population of mice consists of equal numbers of males and females, and at the time of sampling, 60% of the females are pregnant. A biologist studying this population randomly samples 5 mice. What is the probability that exactly 2 are pregnant? Okay, so a couple things to watch out for on this question. The first couple things is there's a couple like coded little hinty type things. So when you're sort of decoding this kind of thing, the first thing I would notice is a large population. That's one sort of important sort of thing. And then, they tell me some numbers. So we got the equal numbers, and then the 60%. So that's helping me think of how I'm going to combine this stuff. And then there's sampling 5 mice and exactly 2. I think those are the important clues. Obviously, we're going to need everything to put it together, but those are the super special math things that if you miss one of those things that is circled or underlined, you will totally not be able to do the problem. So those are the important things we got to combine. And so large population actually means it has a special probability word that goes with it. And sort of, I guess the 2 things we looked at in this course, there's sampling with replacement or without replacement. With replacement. Or without replacement. Okay, and with replacement also goes with this idea of independent. So I always think of it as dice versus cards. Independent, that's close enough. So this is like dice. You roll a dice, and then you roll it again, and it kind of resets, right? It doesn't remember what you did before. But without replacement is like cards, where you have a sort of deck of cards, and you're pulling from the deck of cards. And if you have a population, sometimes it can be without replacement, like you pull people out of the population, and you don't put them back in. And sometimes it's sort of independent. Which is it here? Well, the secret is because it's a, quote, large population, you're thinking the population is so big that when you pull somebody out of it, the population is so big it doesn't really change the odds. So this is a secret code word that means sort of independent. So the status of every individual mice, of our 5 mice, that's horrible. Independent? Okay, I don't know. The status of these 5 mice, what happens to one mice does not affect what happens to the next mouse, and so on. And that's because the population is large enough that it sort of doesn't matter. That's what large means. So that's one thing. So we're going to be taking these 5 mice, and the status of each of the mice is going to be independent of all the other mice in the population. The next part is sort of putting together this one, the equal numbers and the 60%. And to me, this one is a probability tree. So I look at that, and they say they're telling me 2 things happen. So first, there's male or female, and then we're sampling 60% of the female. So I guess it's the of the. Anytime you have a proportion of some subpopulation or if-thens, to me, this is a probability tree. So these 2 parts are saying equal numbers of males and females, 50% male, 50% female, and then of the females, 60% are pregnant. 60% are pregnant, and 40% are not pregnant. So so I'm doing little shortcuts here for myself. Maybe I could remind myself, M equals male, F equals female, P equals pregnant, and then I'm right, NP equals not pregnant. Okay. So that's the little probability tree that goes to the first bit. And from this probability tree, I can see the probability of a mouse being pregnant. And the reason I care about pregnant is because later on, we want to know pregnant or not pregnant. I could say the probability of any individual mouse, probability of mouse is pregnant, is, by the multiplication rule, 50% times 60%, which is also known as 30%, or 3 out of 10. And this is the probability multiplication rule. So that's what I'm sort of taking out of this probability tree. Any questions or comments so far? So far, I think if the hard part of this question is also that it sort of combines 2 things. You sort of have to do all the stuff with the first part. That's what we've done. And then you have to, we're going to do this one in 1 second. But we've done the first sort of half in the blue box. And we're just going to use that to solve the last little bit, which is the actual question. Questions or comments so far? It's OK? OK, let's do the next part now. So what is the probability that exactly 2 are pregnant? And this is where it's quite easy to make life difficult for yourself. So if you're thinking, okay, there's 5 mice, each mouse gets a probability tree, and then I want to stack up 5 of these trees. Like you could take this tree, you could say this is the first mouse, then do like another tree with the second mouse, then another tree, then another tree. If you draw 5 probability trees, you're going to have a bad time. And that's just because it's like so much stuff to do. So I think at this point, you got to combine a technique. The easiest way to do the problem is to combine what we did already, where every individual mouse is 30%, with another technique of saying, okay, if every individual mouse is 30%, we don't need the probability tree anymore. You have mice, you pull them out, 30% of the time they are pregnant. What's the probability? Exactly 2 are pregnant out of 5. So that's what I'm going to do. I'm going to sort of like isolate this part of the problem on its own. And this is the little conclusion that is going to get imported into the next part of the problem. And now I'm going to answer the question of the second part of the problem. What is the probability that exactly 2 are pregnant? So I need 2 mice out of 5 need to be pregnant, 2 pregnants and 3 non-pregnant. So this is the probability that we get 2 pregnant and 3 not pregnant mice. And this one to me is a combinations problem. Combinations, permutations, it's a counting problem. So the way I think about it, I really like Scrabble words, as you guys know. So the way I think about it is we are working with letters or words of length 5, and we have 5 blanks. Okay, and we have 2 letters that say P on them, and we have 3 letters that say NP on them, right? NP, NP. And we need to come up with a bundle of mice so that the 2 P's are there and the 3 NP's are there. But there's more than one way to do it, because there's more than one way you could put these in order. So this is how I'm thinking about it. I'm going to count the ways with order. And so, for example, I could do, maybe this NP goes here, NP, this NP goes there, NP, this NP goes here, that's NP, and then these P's go here and here. So this is like one of the ways. And you could think about it for a long time to try to figure out what's going on. But if you remember what we did in class, if you have 5 slots, there's 5 places for things to go, you can choose 3 of those slots to put the NPs down, and then the P's have to go anywhere else. So in total, there are 5 choose 3, which is 5 times 4 times 3 over 3 times 2, which is 10 ways. 10 ways this can happen. So in other words, when we're thinking of these as individual outcomes, an outcome is some sequence of P's and NP's. The types of outcomes we're looking for, well, there's 10 of them that would all lead into this event of 2 pregnant and 3 not pregnant. Okay, so the probability, so therefore the probability that we are looking for, get 2 P's and 3 NP's, it is 10 times the probability of any individual outcome. And the individual outcomes here are any one like this. I'm going to, just for simplicity, I'm going to do the one that's in order. The probability of first mouse is P, second mouse is P, third is NP, fourth, let's write it all up. Fourth is NP, and fifth is NP. So in other words, there's 10 outcomes that all kind of look like this, where you have 2 P's and 3 NP's, but in some weird order, and they're all equally likely. So if I want to count up the total probability, it's 10 times the individual probability. And now I have to figure out the probability of this. And this is where we import the fact. So maybe I drew the arrow prematurely. We import the fact. By independence, these things can just get multiplied by independence. So this is 10 times the probability of first mouse is P, times the probability second mouse is P, times the probability of the third is NP. Okay, and we're going to save a little bit of writing with a dot, dot, dot. Probability times the fifth is NP, which is 10. Each of these we determined is 30%, so this is 0.3 squared, and the other one over here is 0.7 to the power 3. Each of them is 0.7, and there's 3 of them. So that is the final answer that I got. unless I made some kind of mistake. What do you guys think? Anyone have any questions or comments? So did I do it right, first of all? Now you got to put it in your calculator and see. I guess we can look at the answers, which I did not open the answers, which was silly of me. Let me also open the answers. Practice questions, practice solutions. Okay, here we go. This was question number 44. Let's see what it says. Okay, so the final answer that they got, we'll sneak it in at the top of the screen here. No, we won't. The computer won't let us do that. Let's try to do this. Okay, so here is a similar kind of paragraph of text, similar to what I did. But the final answer they got is 5 factorial over 2 factorial, 3 factorial. That's the 10. That was the 10, 5 choose 2, or 5 choose 3, which is 10. And then times 0.3 squared times 0.7, which is, I guess they're telling us, is 0.3 something, 0.3, 0.3, dot, dot, dot. Okay, I don't know. Okay, this is a good one. Yeah. 5 choose 3 and 5 choose 2 are the same number. So if you say, why is it 5 choose 3 and not 5 choose 2, I would say you could have done either one, and it would have been fine. And again, it's just 2 equivalent ways of thinking about filling in these slots. You can either fill in, say there's 5 slots, I pick 3 to put the NPs, and then I'm done. Or you can say there's 5 slots, I pick 2 of them to put the P's in, and then I'm done. Either way, they are equal. Yeah, great point. 5 choose 3 equals 5 choose 2 equals 10. They're both equal. In fact, it's always true that if you do like n and choose k, it's always equal to n choose n minus k. So if you sort of like flip the number on the bottom, it's still equal. And that's again because you can either think of choosing one type of thing or choosing the other type of thing. And whatever, when you split it up into 2 groups, you can pick the left group or the right group. Great question. Anyone else? All right, let's do a show of hands. Who would, if this came up on the midterm, would feel pretty good about this kind of problem? Yeah, okay, great. So I think it's like a pretty bread and butter one. Actually, I will say the hard part is this is really 2 problems in one. This was sort of one kind of easy problem. This was another kind of straightforward problem, and you have to know to combine them. That is maybe the tricky part. Yeah. How do I know to use 3 and not 2? In the 5 choose 3? Yeah. Oh, I'm saying you could have done it either way. Both are correct. Both are perfectly correct. And in fact, so this shows you they're mathematically correct, right? They're equal. You get the same final answer. And it's also perfectly logically correct to say I'm choosing 2 of the things instead of 3 of the things. 2 equally good ways to do the problem. Yeah. Okay, let's do another one. What else was there? Okay, let's do, so we did, this one kind of had an unordered counting. So let's save this one for now. Let's do, I guess the practice test didn't have solutions. So maybe I should do practice test number 10 so that you have a solution for that one, which will be somewhere over here. Okay, I gotta find it. Okay, here's the test. Practice test number 10. What is the probability that 2 turtles selected are the same species? Okay, this is one of those ones where you have to read the thing. A large wetland consists of many turtles. 60% are species A, and the rest are species B. And there's more males or females depending on the 2. Okay, great. So this is another one where same kind of difficulty. In this sort of question, for any individual turtle, it's going to be a probability tree. And then we're using the probability tree to do something. This is a good one to follow up with. Let's do it quickly. So let's copy this one in. Okay, so once again, this is a 2-part problem where the first part is to do a probability tree. The tree looks like this. I guess maybe I can do it here on the side. Will it let me move this now? I have to select it, I guess. Okay, so there's species A, and species B in my probability tree. And then it splits up as 40 to 60 females, so female, male, and this is 40%, and this is 60%. Species A is 60%, okay. And species B is 50-50. I guess this is 40, and then this one is 50-50. Okay, so there's the little tree that goes with the story, unless I made a mistake. This is always good to double check. And then from this, you can calculate, for example, the probability that a turtle is female equals the sum of two things. There's two paths. So I would sort of highlight them like this. So it could be female like this on the top branch, or it could be female like this in the middle branch. But either way, it's going to get added. So 0.6 times 0.4 plus 0.4 times 0.5. And you got to work that out. So 0.24 plus 0.2, 0.44. Unless I'm doing math wrong in my head. But that looks good to me. Okay, and then so the probability of male will be the opposite, 0.56. So this is, again, we've done the first part of the problem, just taken everything that we need from the first little bit. We haven't even touched the second bit yet. And that second bit, we're going to use, just import this one fact. We're not going to draw a giant probability tree with like 100 branches. We're just going to take what we have here, take the final conclusion, and import that into the next part of the problem. That's what we're doing. Someone tell me, did I make a mistake here, or is this approximately correct? No one is yelling at me, so I'll assume it's OK. So now we got to do two turtles at random. And what is the probability? They are the same species, but different sexes. OK, well, I guess in my little thing here, I didn't include the species. So this is slightly annoying. I guess I really need all four probabilities then. So OK, like we gotta split it up further. So there's let's say an A female and a B female. And I just have all the four probabilities. So this one is this. This one is this. This is 0.24. This one is 0.2. And then I got an A male and a B male. And a B male. And they're going to be different numbers. What are they? An A male is 0.6 times 0.6, which is 0.36. And a B male is 0.4 times 0.5, which is 0.2. OK. So that looks good. OK, so now we have these four things. So I lied to you before. We actually need the species, because we need same species but different sexes. And once again, this is some kind of combinatorics problem where it's not really combinations or permutations and chooses. It's just kind of like listing out what's going to happen. And the things are sort of combinations of the possible ways. So same species, different sexes. They could either be species A or species B. If they're species A, I think it could go A female, A male. That's one way. It could go the other way. A male, A female. Or it could be the reverse. So let's say ways it could happen. Ways it could happen. So I'm thinking of them in order, the first turtle, the second turtle. So we could have an A female, then an A male. We could have an A male, then an A female, and the same thing with the B's. B female, or B male, the B male, or the B female. And I think those are the only options. Sometimes it's good to have sort of, you try to think of what could I possibly have missed. So it's got to be either species A or B. There's no like species C anywhere. And I've done female male and male female. Those are the only ways you can have different sexes, so one of each. So I think I got them all. And in this case, I guess it was just like logicking through it. There's no formula, like the combinations and permutations that are a shortcut. You just got to think of the ways it can happen. If you want, it's like basic counting. And now I got to add them all up. So the fact that I'm going to use is independent. I'm going to use independence again. So the probability of first turtle is something times the probability, let me say, the probability of both happening. First turtle is something, and the second turtle is something else, is the product. So this is by independence. We can write, anytime we have two turtles, we can write it as a product of the two individual turtle probabilities. And so when I have a female, a male, that splits into the product of two things. So when I go to calculate the probabilities, I will have to add up over the 4 different ways, and I will have to multiply the first turtle and the second turtle in each of them. So this will go to, this becomes, so probability, let's say, instead of calling it, let's call it the event. What weighs the event? Where the event is this thing. Call this thing the event. So the probability of the event is the sum over 4 things, and each thing is a product of 2 numbers, and the 2 numbers I import from over here. So the probability of a female, a male is 0.24 times 0.2, right? So now I'm importing the answers. These numbers get imported over here, and I'm doing 0.24 times 0.36. Okay, good. Got the right number. Plus a male times a female is 0.36 times 0.24. If you were also if you were thinking about it a different way, you might have a factor of 2 instead of adding the same number twice. But I think it's a little bit conceptually clearer to list out all the ways like this. Of course, there's more than one way to puzzle it out. And then last but not least, we got the species B. Female, male is 0.2 times 0.2, and then plus another 0.2 times 0.2. Okay, so it's a sum of 4 things. Each thing is a product of 2 numbers. And you would type it in your calculator and crunch it, and then get a final answer. I am not going to put it in my calculator. I'm just going to leave it like that. And 68. Radar. Radar machines are used by the police to catch speeders. For a radar machine that is defective, the probability that it fails is 0.9. For a radar machine that's working properly, the chance that it fails is only 0.2. Past experience shows that only 0.7% of new radar machines work properly, and 30% are faulty. Okay, great. This is a classic probability tree problem, I think. Let's put it into our work over here and sort it out. Okay. So it is easy to get sort of bamboozled by the wording. So you got to know what to keep your eye on and what's going on. So my first thought when I look at this, I'm like, there's 2 types of things, and then some of them are one way, some of them the other way. So I'm already thinking like probability tree. This is some kind of like if-then, if it's working or not. And then it sometimes can be distracting on like what are the actual categories. But let's kind of break it down and see. So the machine is defective. Is defective is one hint, right? Is defective. And for a radar machine that is working properly, the chance that it fails. So these are if statements. If it's defective, then the probability is 0.9. If it's working properly, then the probability is 0.2. These are conditional probabilities that will go in our probability tree. So we have sort of like 2 states. We have defective, and we have working properly. And presumably these are, based on the wording, properly. These are the only 2 things that can happen. Either it's defective or working properly, just based on the way the question is worded. And so in this one, it's a 90% to fail and 10% to pass. And from working properly, it's 20 and 80, but the other way. So 20% to fail and 80% to pass. So that is what I took out of these first 2 sentences. And it is kind of like a skill. When you like do enough of these problems, you sort of know how to read it and figure out. And I think that's sometimes overlooked. Is like reading these word problems can be tricky. Okay, everyone with me so far? Questions about the first 2 sentences? All right, in the next sentence, it says, past experience shows that only 70% of new radar machines work properly, and 30% are faulty. So the next sentence, this 70% and 30% are telling us we have these 2 branches. So 30% are faulty, which I guess is a synonym for defective over here, and 70% are working properly. So this is the full probability tree. The first sentence gives you the second half, and then this sentence over here gives you this one. Okay, now we have to parse the question. When a new radar machine produced is tested, it fails the test. So this is, again, coded language. It fails the test. When is tested, it fails the test. This is a conditional probability. we are given that it fails the test. So given it fails test. Fails test. So that is the way I would understand this little thing. And then what is the probability that it's actually working properly? So what we actually need to do is the probability of working properly given it failed the test. Okay, and that, I think this is like 99% of the work has been done of like drawing the probability tree and decoding the word problem. It's very easy to get confused on like, hey, working properly, is that the same as defective? Like, or working properly, is that the same as like pass the test? You know, like it's easy to get mixed up on these things. And so you gotta kind of read it carefully. I think that's the hard part. Okay, I will do the calculation in 1 second, but questions or comments about how we decoded it? Now it's like a very, once you've gotten to this point, it's like a straight shot, like shooting fish in a barrel. It's like very, very bread and butter, not much left to do. I think we did all the hard work already. It's okay? All right, let's do it. So working properly given you failed the test. Well, failed the test, there are 2 ways. So failed the test, it can either go like this or like that, okay? And then working properly, there is only one way. Working properly, there's just one way, because it's got to be this branch, right? It's working properly and it failed. So you could write out the formula, probability of working properly and failed, and then divide it by the probability of failed, which in this case is the sum of 2 things. So the probability of working properly and failed is 0.7 times 0.2, and the probability of failed is 0.7 times 0.2 from that branch, plus an additional 0.3 times 0.9. So that is the final answer that I got. It is always a good check when you're doing these types of problems. The bottom, usually the top will appear in the bottom somewhere. So like 0.7 times 0.2 appears over here. So that's a good sign. If someone said, what's the probability it is defective given it failed the test, that would be the 0.3 times 0.9, and altogether that would sum to 100%. So that's a good sign. Once again, you got to put it in your calculator and see what is the closest answer if it's a multiple choice, but that is the right answer. Okay, so yeah, once again, I think the hardest part of that problem is the reading and converting the text into the probability tree and what you actually want to figure out. Okay. Questions about that one? All right, should we do yet another one? Okay, let's see. What did we do? We did that one. We got to start checking these off. This one. The one we did was 68. WOct8F was, we did one with counting already. So what was 45? Let's do 45. Okay, yeah, this is a good one. So yeah, this one is also combination-y. A litter of mice contains 8 mice, 3 males, and 5 females. So once again, my brain immediately goes to Scrabble tiles. We have 3 Scrabble tiles that say M. We have 5 Scrabble tiles that say F, and they're all in a bag hanging out together. So we got M, 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 and then F, 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 F. And any kind of like sampling we're going to do, I just think of it as combining these things in a different way. Okay, 3 mice are selected for rearing in another room. So to me, we're going to pick them in order like this and say there's the first one, the second one, and the third one. Of course, you could do it not ordered, but I find it easier to do it in order, and I will just get some factor at the end of mixing it up. So we have 3 slots because we are choosing 3 mice. So let's color code this. So 3 mice are chosen. Those are the 3 slots over here. Okay, what is the probability that we have at least one of each sex? So we have both a male and a female in our sample of 3. And you could start listing out words, and then we're going to have to count the number of ways and things like that, and probabilities. So that's one way you could do it. Here's a fact. There are 8 possible 3-letter words. And the reason is there's 2 choices for each. So the first one can be male or female. The second one can be male or female. And the third one can be male or female. So there's 2 times 2 times 2 by the basic multiplying rule we did. So male or female, et cetera, for each choice, which is 8. So we could write out all these 8 possible combinations of males and females that we can get here. And we need to count the words that have at least one of each sex. So that would be like 2 males and a female. And you could start writing them out. So you could do like male, male, female, male, female, male, male, female, 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 male, male, female, male, female, 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 male. Those are the ways. If you haven't spent as much time with these things as I have, it can take a while to come up with this list of 6, and it can be quite annoying. Maybe you like write one down twice, or you like forget one. So it's kind of a long list, and it's kind of annoying. So this is like one way to do it. We write this down. But actually, there's an easier way. There's an easier way. Does anyone have a or have a hint of what the easier way is? Yeah. Yes, that's very good. So you calculate the probability that it's all one sex. And in fact, look, I listed 6 of them over here. There were 8 possible total ones. So I'm missing exactly 2 things. And so this is at least one of each. At least one of each. And so this takes a while, and it's a long list. But the other list, which is not at least one of each, not at least one of each, that one is easy. Because not at least one of each is only 2 things, male, 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 or female, 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 right? So in this problem, you got to calculate the probability of this. It's annoying. There's 6 of them. You would have to figure out the probability of each one of these things and then add them up. The probabilities are not all equal because having 2 males is different than having 2 females. So things are annoying. You could definitely do it this way. Writing out the list is annoying. Calculating the probabilities is annoying. But this one is way easier. So this is calculate the probability of not at least one of each. And then you could convert it to this one because they have to sum to 100%. So in this problem, just because of the way the counting worked out, it's easier to do the reverse, calculate everything except for what we wanted, and then do 100% minus it. There is no good answer to when should you do the reverse. Do the reverse when you think it will be easier. That's the answer. And in this case, I think it's a lot easier because 2 is less ways than 6. So the way I'm going to do it is I'm going to do the reverse. So the probability of at least one of each. I'm going to do 100% 1 minus the probability not at least one of each. Okay, and this is something we know from our Venn diagrams you can always do. And in this case, not at least one of each is split into 2 groups. It's either male, 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 or female, female, female. And I can add those probabilities together because they don't overlap. So I got to do the probability of male, 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 and the probability of female, female, female. You could write out male, 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 and female, female, female. You're going to have to write out, you can think of doing some big tree. Okay, let me write out the answer, and then there's a bunch of different equivalent ways you can think about it. So male, 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 the first male is 3 out of 8. The second male is 2 out of 7, and the third male is 1 out of 6. That's male, male, male. Female, the first female is 5 out of 8. The second female is 4 out of 8, 4 out of 7, and the third is 3 out of 6. So that is like the correct answer. And the way I was thinking about it was a probability tree, where you say like the probability that the first is male or female, and then the second is male or female, and the third is male or female. So like a little probability tree like that is what I had in mind, and when I came up with this answer. But you could also do it by combinations and permutations, like 3, 2, 1 is 3 factorial. 5, 4, 3 is 5 falling factorial with 3. So you could also write it out in terms of words and just counting the number of ways you can make male, male, male with these things. Either way, you should get this as the answer. OK. Yeah. I like the probability tree for this one. So I need to get male, male, male. So on the first one, I need to get male. That's 3 out of 8, and then so on. So this is like the earn problems where you count how many balls of each type are left in the bag. OK, let me finish writing this. 2 out of 7, 5 out of 7, and then 4 out of 7 for the last one. 4 out of 6, and 2 out of 6. No, 1 out of 6. 1 out of 6. Yeah. OK, great. OK, that's my little treat. OK, that's the answer to this question. That's how I would do it. Again, perfectly correct to do it this way with writing out all these things, finding the probability of each of them. It's just way more work. So it will be correct, but you want to do it in the easiest way possible. OK. Questions or comments about that one? All right, let's do WOct as the last little thing, WOct. And I'm going to just answer the last part. So you roll 5. Let's call them 6-sided dice to keep it classic, 6-sided dice. What is the probability of a triple? So the probability of a triple. And a reminder, a triple means you have 3 of a kind, means 3 of a kind, but not 4 or 5 of a kind. 3 of a kind, but not 4 or 5 of a kind. So in other words, you have 3 of a kind, and then you have two other dice. And in the actual mathematized question, there was like scaffolding to get up to this. So this was part C, and there was part A and B that were supposed to be hints for this one. But I'm going to go straight to the hard problem of this. And the way you have to do this problem is kind of the way we derived all the combinations and permutation things, is you look at the sequence of choices that you have to make such a thing, a triple. And then you multiply all the choices together. This is like how we did everything. Like, this is why we had multiplications in our things. And so the way I think about it is, again, we have 5 slots. I'm going to make a little thing with my choices up here. And then I have my 5 slots. And what I'm going to do first is we have a triple. I'm going to choose what are we going to have a triple of. So there are, we're going to first decide what number will be the triple. Okay, and there are six options. 6 options. It could be 1 or 2 or 3 or 4 or 5 or 6. 1, 2, all the way up to 6, because it's a 6-sided dice. In the mathematized question, they first had you calculate it assuming that this number was a 1, and then you were supposed to realize that, oh, there's actually 6 choices for that. So that this got added on at the last second in the mathematized. But there's 6 options for what number will be the triple. And then you can kind of think of, once I have chosen this, I have my 3 copies of that thing. So let's pretend, for the sake of argument, that I chose 1. Then I would have 3 1s floating around over here. And I have to put the 3 1s in my 5 slots. And so that's what I'm going to write down as my next choice. So there were 6 choices for this, 6 choices for this. Let's say we get a little number of choices. And then next up, I have to decide where to put them. Where to put the 3 copies in the 5 slots. Right, so I have my roll of 5 dice. I have 3 copies of my number, and I have to import them in. That is 5 choose 3, just like we did in the first problem, also known as 10. And that is saying now we can put them in somewhere. Maybe they go here and here and here. I don't know. OK. So we have our 3 1s, but there's more than one way you can have 3 1s, even with these particular things, because there's other options for what can happen here and here. So that is the next thing we got to choose, is what is going to happen there. So, and the way I think about it, there's lots of equivalent ways to do it. I'm just going to go left to right. There's one slot that is the leftmost slot. There's one slot that is the rightmost slot. And I'm going to choose what number goes in the leftmost slot and what number goes in the rightmost slot. What goes in leftmost slot and what number what goes in the rightmost slot. Okay, and it's very easy to make a mistake here to think there's 6-sided dice, so there must be 6 choices, but there's actually only 5 choices, and that's because whatever you chose in the first choice is forbidden, right? You're not allowed to have a 4 of a kind or a 5 of a kind. So there's actually 5 choices for each of these. 5 choices. 5 choices. And so it's in my example, you can only pick 2 through 6. 1 is forbidden because you chose 1 before. Maybe you pick a 6 for this one, and then this other one, there's also 5 choices. 2 through 6. They do not have to be the same, but they could be the same. So maybe we pick 2 over here, and then we put them in. So so this would be 6, and then this one would be 2 in my example. They could be any numbers. So that's the sequence 6, 1, 2, 1, 1. That is one of the possible ways it can happen. And if I have accounted for all the ways in my choices, then I will get all the possible things. So there's 5 ways and 5 ways to do these things. So there were 6 choices for what is going to be the red number. There were 10 choices for where do I put the red numbers. And then there were 5 choices for the green number, 5 choices for the light blue number. And if I combine all these by the multiplication rule, I can make a choice here and then make a choice here, and I can do any combination of those choices. They all multiply. So therefore, the total number of ways, just like we did in class, is the product of all these things, is 6 times 10. Let's write it as 6 times 5 choose 3 times 5 times 5. And that is the total number of ways we can get a triple. To get a triple, thinking of them as in order of rolling the dice. What are the total number of ways the dice could come up? Number of total ways dice could come up. Is 6 to the power 5. 6 times 6 times 6 times 6. That is all the sequences of length 5 on the 6-sided dice, and therefore the probability is the ratio. Therefore, the probability of a triple is this ratio. 6 times 5 choose 3 times 5 times 5 divided by 6 to the power 5. If you want, you can cancel out one of these 6s to get a nice number. So 10 times 5 times 5 divided by 6 to the power 4 is the final answer. You could simplify it a bit more, but let's leave it like that. Questions or comments about this one? I think this was the hardest combinations problem we had you guys do. Okay, we'll stop there. I'll be around for a few minutes if you have some last-minute questions, but otherwise, good luck on your midterm. I think if you studied, you will do well. It is a very doable exam if you have studied the problems. All right, good luck.